I hope you all are fine and you are consistent with your learnings. Uh, Today in this video, I'll be talking about Wiens-Bridge oscillator, and uh, obviously we are making use of operational amplifiers here. Now, to start with, this Wiens-Bridge oscillator, it's basically used uh, to have maintained oscillations, audio frequency oscillations. And in the beginning, this oscillator was used. It was used for measuring the input impedances of the systems. And to start with, let's draw the circuit diagram for this Wiens-Bridge oscillator. What we have is uh, let's go with first the bridge, uh, and then let me have the operational amplifier, right? So this is the negative terminal of the operational amplifier, and here we will have the output, and here we have a resistance. Say this is R4, and here we have another resistance. Say this is R3, and here we have a series RC oscillator. And let me assume that this capacitor has a capacitance of C1, and let me have this R1 as the resistance of this resistor. And then to close it, we have a parallel RC oscillator. Okay, it has to be like this. So let us assume this is R2. So R1, R2, R3, R4, and let's assume that this capacitance is C2. And the output of the operational amplifier is connected to this bridge. Say this is point P, and this bridge is grounded here. And then going with the positive terminal of this operational amplifier, we have to connect it to this junction, right? So that everything is grounded, and we can see, yeah. So clearly, one thing is clear here, that we have a bridge here, and this bridge is acting as a feedback circuit to this operational amplifier. And as we know that the negative terminal of this operational amplifier inverts the phase of the signals, and the positive terminal does not. So this is a situation here. We have 4 arms of this bridge. We have plain resistances R3 and R4, and we have two or C type of situations here. One is the series combination of R1 and C1, and another is the parallel combination of R2 and C2. Now, this circuit certainly, if we want the sustained oscillations in the output of this operational amplifier, in that case, it should certainly satisfy Borg-Huson criteria. And we better understand what Borg-Huson criteria is. That may be used later on. So for now, we can have the realization that we have a feedback circuit in the form of a bridge to the inverting side of this operational amplifier. Now, the right thing here would be that if we can break down this circuit into a simpler one, where we can make some calculations. So, if we think of drawing this circuit into an equivalent circuit, we'll try to do that. Okay. So we'll go with the operational amplifier like this, and this is the negative terminal, this is the positive terminal, and this is the output. Okay. Now, if I choose a resistance here as R4, okay, and this is the negative terminal of this operational amplifier, and if I connect it like this, and I should call it, this should be my what it should be, this should be my R4, and this should be my R4, and this should be my R3, right? And now what should I do? I should go with this terminal and look for the series combination of C1 and R1. This is R1 and this is C1, and I can connect it back here. Then I can have a parallel combination here. Oh. And then ground it. So this should be my R1, this is R3, this is R4, and this should be my R2, and this should be my C2. Now here is a simpler version of the circuit that we have shown. Both things are equally equivalent. Now you can connect these grounds so that we have the overall configuration same as that of the original circuit. Now let us boil down this. Let's boil down this circuit where we can make use of the output that we have, and we are subjecting that output to the 2RC type of situations. So in order to do that, let's move on with an assumption here that we have a capacitor, we have a resistance, okay, go like this. Then we have the parallel combination. This is a capacitor here, and this is the resistance. Close it, and Now, this is the output, part of output of the operational amplifier, and this is the V feedback that we are subjecting back to the operational amplifier. And this is my C1 and this is my R1, and this is my C2 and this is my R2. So we have taken the output of this what we call as the operational amplifier, and we are trying to calculate we are trying to calculate the VF here, the output voltage that we are talking about. Now, to make this situation simple, we would like to ensure that so that our calculations are simple. To make our calculations simple, in order to get the condition for sustained oscillations in this Wiens-Bridge oscillator, we would go with the assumption that that R1 is equal to R2 is equal to R, right? And let us assume that this C1 is equal to C2 is equal to some C, right? Now let's analyze this thing that's in front of us. Now in this case, we have two RC situations. One is series one, and another is the parallel one. So let me calculate the impedance of the series one first, and then I will calculate the impedance of the parallel one. So to start with, let's talk about let us assume that ZS it is the impedance. It is the impedance of series RC combination. Now this is clear to us that since this is C and this is R, so what will be the impedance in this case? The impedance in this case will be, so let us say this is 4 now, that will be ZS is it is, what is it? It is XC. It is capacitive reactance of the capacitor plus R, because we have kept every resistance in this circuit equal to R. So to proceed, we understand that this XC we can write in terms of a complex number. That's 1 by J omega C. Well, J is exactly same as that of iota that we are making use in complex numbers. So it's just a mark of differentiating the field here, that we are doing it in electronics. So here we are using iota in the form of J. So everything that goes with iota in the complex numbers, the same thing is going to happen with J in case of these electrical networks. So if this is the case, then we can calculate this ZS. It must be 1 upon J omega C plus R. Okay, we can have the LCM of J omega C here, and then we can have 1 plus R J omega C. Now let's call this equation 1 for the time being and see where we can reach after this. So now the another important thing is that we have these we have the parallel combination of what we call as this capacitor and this resistance. Now they are in parallel. Now if they are in parallel, we want to measure the equivalent impedance of this circuit. So for that we understand that let us assume that we have ZP now. Now if we have two resistances in parallel, then we have a result like what's the result? The result is like R1 R2 divided by R1 plus R2. Now let us first write down this what we call as the impedance in the parallel combination. So XC and R is the point here. Here this is C and this is R, and this is C and this is R, right? So we can have here capacitive reactance, that is XC times R divided by R1 plus R2. This is XC plus R, right? So now we can make use of the things there. What is XC? This is 1 by J omega C R. So R is here. So this is this is divided by XC. What is XC? That is 1 by J omega C plus we have R here, right? And we can write this as, this is R upon J omega C, and we can have an LCM here and we can multiply it. Then this J what will happen here is you will have this whole thing if you multiply it. So here I have to calculate this this LCM here. That will be J omega C and R. So this is 1 plus J omega C R. Now when you will convert it division into the multiplication, you will get J, it will go up. This is J omega C R divided by 1 plus J omega C R. So here I think here is a possibility of some cancellations. This C and C will cancel, omega and omega will cancel, and even this J and J will cancel. So what we are left here is in one case we have calculated ZS, and now we are going to calculate ZP. So what we have here is ZP. Okay, what is ZP coming out to be? So ZP is coming out to be it is R upon it is R upon 1 plus, this is R upon 1 plus J omega C R. This is 1 plus J omega C R. Now this is ZP, and we have ZS, and ZS is here, right? Now if we go back to the situation that we are talking about, we can think in terms of voltage divider rule. I mean, if we want to apply the voltage divider rule in this case, what we have for that is, if I have, say for example, I have the V feedback. Okay, now this V feedback, it's going to be what? It's going to be ZP divided by ZP plus ZS times the output voltage. That should be the situation here. So in order to do that, so applying, I would write here applying voltage divider rule. Okay, when we do that, we will have VF equal to ZP divided by ZP plus ZS times V out. This should be the case, right? Now all we have to do is we can write this VF by V out as ZP upon ZP plus ZS. Now this VF by V out, this is, let's assume this is equal to beta, right? So let's go with beta here. So this implies that beta is ZP divided by ZP plus ZS. Now we want to substitute the values from equation 1, 2 into equation 3. So let me call this 2, right? So I have 1 and I have 2 and I have 3. So now what am I going to do is to substitute 1 and 2 in 3. Now let us see what comes out of that. Okay, so this is my 5. So what's going to happen? Now I'm going to go with beta, right? So beta will be, okay, using that, what I'll get, I'll have R divided by 1 plus j omega c. Okay, this whole thing is divided by R by 1 plus R j omega c plus 1 plus R j omega c divided by j omega c. So this is the case here, right? and let's proceed from here and see where we will reach. Okay, so let's go from here. What we're going to get is you have beta equal to R by 1 plus j omega c. Then this is divide by, okay, you will have 1 plus R j omega c times j omega, right? So here we will have R j omega c, and we'll multiply this with, this is plus 1 plus R j omega c whole squared. I think it's clear, very simple. So now we will turn down, so beta is 1 R by 1 plus j omega c times 1 plus R j omega c times j omega divided by, yeah, what is it? R j omega c plus 1 plus R j omega c whole square. I think it's fine up to this point, right? And let's move on. Now what is important at this point is that we have to go back to the Barkhausen criteria. And what is Barkhausen criteria? Barkhausen criteria says what it says. It says that for sustained oscillations in the oscillator, this A is the gain, A beta, its magnitude should be equal to 1. So this is the necessary condition for having a situation like that, where we can have sustained oscillations. So this thing, the product of A and beta, must be equal to 1, where A is the gain, it's the voltage gain. So let's proceed from here and see where we are going to reach. Okay, so when we do that, so what's going to happen? Anything that we have here is, do I have any kind of what we call as cancellations? You can see here, this is 1 plus j omega c, right? And here I have j omega. Where is the c here? Where is, it must be j omega c. It must be where from this has come. So this is j omega c. All right. So this is j omega c, And when we proceed now, what we have to do now is to uh, is to go on using Barkhausen criteria to evaluate this thing, right? So in order to do that, let me check here. I feel something is having some kind of problem. Now here it is ZS, that's okay, and here it is ZP, fine. And what's going to happen from here is R J omega. What is this? Is R? Okay, this is R J. Where from this R has come? This is 1 plus R J omega C. Where is it going? Where from this R is coming? Now, if I see here, I have this thing. This is R. Yeah. Let me check that first. What is that? That is okay. What is that? Is 1 plus R J omega C by J omega C. 1 plus R J omega C divided by J omega C is correct. Okay, then ZP. What is ZP? It is R by 1 plus J omega C and R. That's correct, right? So when you convert this into the multiplication, what we are going to get here is this is the division. This is R J omega C is correct. Then plus 1 plus R J omega C whole square is also correct. So this is going to come down here. R J omega C plus 1 plus R J omega C whole square. Okay. And this has to go up. Now this has to go up. So this is J omega 1 plus R J omega C. This is 1 plus R J omega C. So why is there something? This is how can I go back here? Now this is here it is J omega C. It has to be J omega C, and 1 plus R J omega C. 1 plus R. Okay. Here. I think the mistake seems to be here. So let's go back here. Yeah. Here. This should be R. Now this R J omega C is here. This is R J omega C is here. And then there is a problem. Now how do I have R J omega C here? Because here I have R by 1 plus, okay, here it's only J omega C here, right? I think that there is the problem. Let us see. So if that's the case, then what we will come up with is here I will have 1 plus J omega C. So this 1 plus J omega C, I might have committed some mistake. I'm not sure. Now let me try to come to the result of this formulation. Otherwise, this whole thing will become futile. So you can check it yourself. So what we are going to get from here is, say this is 6. Okay, we will have this Barkhausen criteria, that is a beta, and this must be equal to 1. Now a is okay, I am okay with a. And what is beta now? What is beta that finally we have got? That is r j omega c divided by r j omega c plus 1 plus r j omega c. Here we have whole square, and this whole thing is equal to 1. This whole shit is equal to 1. So we can take it there, and this is a r j omega c equals r j omega c plus this is 1 plus r square j square omega square c square, and then plus twice rj omega c. Okay, I have opened this whole square thing, and finally we have this equation, and I want to exploit this equation making use of coefficients. Now the very first thing I would like to do is is to equate these equations real numbers. I mean, okay, so if we see from this equation is a combination of real numbers and complex numbers. So here this is j square. As I said, this j is same as that of iota. So instead of when we kill this j square, we will have minus here. We're going to have minus here. Now let's think in terms of equating this equation in terms of the complex numbers and what we call as the real numbers. So do we have any more manipulations? If we think we can have we can do it that way. Then now let us put here, this is here I have a complex number, and here I have a complex number, here I have a real number. So if I make a comparison of coefficients of real numbers, in that case what am I going to get is 1 plus r square omega square c square will be equal to this will be equal to 0, right? It is not plus here, it is minus. So r square omega square c square will be equal to 1. Now can we proceed from here? I think we can. We can calculate the frequency of oscillation. This is omega square is 1 by r square c square. So omega will be 1 by under root of rc. Okay, from here we are able to calculate the frequency of the oscillation that we can make use of. That we can make use of, and with this proceeding on, if we go on from here, comparing the imaginary parts of this equation. So if this is my 7, comparing imaginary parts. imaginary parts. So what's going to happen here is we have to write down the equation in terms of the coefficients of imaginary parts of this equation. When we do that, what we get is we will get something like this r omega c plus r4 by r3 r omega c is equal to r omega c plus iota r c omega. Now the question is where from this R4 and R3 has come. If we go back to the circuit, if we think in terms of this is a negative terminal, then we have a resistance here. This is R4 and this is R3. And we have closed loop gain A. That is always equal to 1 plus RF by RI. Now RF is here R4 and RI is here R3. So this is why you are able to see this. So I have used for A equal to 1 plus R4 by R3. So this is how the equation has been compared, and from here now things can be simpler. So you can have something you can get out like R omega C 1 plus R4 by R3 equals R omega C. It's equal to R omega C, right? This is R omega C. Now, if that's the case, you can have cancellation of this R omega C with R omega C. Now here, if we think here, I think here we should be looking for this RC omega, right? RC omega. What was here? Come on. Here it was 2RJ omega C. So here we will have R omega C times 1 plus 2. So this R and omega and C is going to cancel. So this is 1 plus 2 is 3. So R4 by R3 will be equal to it will be equal to 3 minus 1, that's equal to 2. So R4 will be 2 times R3. So this is how you have to correlate the feedback resistance R4 and the input resistance R3, which is present in the Wiens-Bridge. And if we do the similar analysis, as we what we have obtained already is that suppose if we do the similar analysis for the situation where we have R1 not equal to R2 and where we have C1 not equal to C2, what we are going to obtain is what we obtained for the angular frequency for the sustained oscillation in the oscillator. It is omega is 1 by RC. In that case, we will have omega equal to 1 by under root of R1, R2, C1, C2. So if you boil down this equation as for an approximation R1 equal to R2, R3 equal to R4, then you will come back with omega is equal to 1 by under root of RC. So with this, what we have done, we have tried to understand Wiens-Bridge oscillator using an operational amplifier, how we can have sustained oscillations that can be produced in a circuit having an operational amplifier for obtaining the closed loop gain. And what we did after that, we tried to go for the equivalent circuit of that, the circuit that we had originally drawn, and then we made certain approximations, and finally we we evaluated some of the equations, and we were able to calculate the angular frequency, yeah, the resonance frequency for this oscillator, and we could also analyze that the relation between the R3 and R4, and we could see that R4 should be 2 times R3 for for sustained oscillation, and we made use of Barkhausen criteria to evaluate the resonance frequency and to correlate the resistance R4 and R3.